In addition to finding a confidence interval on the mean, we may also want to find a confidence interval on the variance to find out a range of values in which we would expect the population variance to fall. For variance, we don't use the normal distribution, however. We use a distribution called chi-squared. It looks like x squared, but it actually is the Greek letter chi. Chi-squared is the name of the distribution. And one difference about this distribution from others that we've looked at is that it doesn't run from negative infinity to positive infinity. Remember that our normal and t distributions were symmetric and had their upper and lower limits at infinity and negative infinity respectively. The chi-squared distribution cannot have negative values. So if we draw the shape of the distribution, depending on the parameters, it's going to take on different shapes, but one general shape is something like this, where our lowest point here is at 0, and then possible values going up through infinity. But it cannot take on negative values. In the normal distribution, we had a definition for our statistic. That was our definition for the normal distribution. For the chi-squared distribution, we also have a definition for it that is n minus 1, where n is our sample size, times the sample standard deviation divided by the population standard deviation. So it gives us an idea of how sample and population standard deviations are related for different situations. In order to find a confidence interval, we can use this definition for chi-squared, and we find through algebra and rearranging those terms, we find that our lower limit on the confidence interval is n minus 1 times the sample standard deviation squared, or the sample variance, divided by our chi-squared term at a level of alpha and n minus 1 degrees of freedom. And then our upper limit is the same term, but because our distribution is not symmetric, we express that a little bit differently than we did when we were finding a confidence interval on the mean. Here we find our chi-squared at the upper limit would be 1 minus alpha. We look up that probability, again n minus 1 degrees of freedom, and this has a probability of, this range has a probability of 1 minus 2 alpha, because I have alpha down here and up here at either side of my limits, so that the probability that falls within that range is 1 minus 2 alpha. Now if we look at our table to give us the chi-squared values, say we have an alpha of 0.05, this would lead to a distribution, a confidence interval of 90%. I have 5% below and 5% above. And let's say my degrees of freedom are 10. So I've got a sample size of 11, n minus 1 gives me 10 degrees of freedom. I need to look up in my chi-squared table for the lower limit. I would look up chi-squared for 0.05 and 10 degrees of freedom. For the upper limit, I would look up chi-squared of 0.95 with 10 degrees of freedom. Now remember that the alpha in the subscript refers to the area to the right of that point. So when I look up these numbers, I expect this number to be much larger than this number. Okay, because this number has only 5% of the area to the right. This number is going to have 95% of the area to the right. If we look at the distribution again, if I want to have 5% of the area to the right, I would have to be all the way out here. If I want to have 95% of the area to the right, I would be somewhere down at this limit. So again, that first number, 0.95, This first number is going to be much larger than this number because it's much further out along the x-axis. Now if we look at the chi-squared table, we can see how the numbers are presented. We've got probabilities across the top, degrees of freedom down the side, and the values for chi-squared in the middle. So if I want to find at nu equals 10 degrees of freedom, and I want to find 0.95, that has a value of 3.94. If I want to find at 0.05, that has a value of 18.31. Again, 0.95, 3.94, and 0.05. Those are the values that I would use in my formula up here, given my sample variance here and here, along with the number of samples minus 1, and then the denominator I would have these two values of chi-squared to determine a 90% confidence interval based on those values.